Welcome back, everybody. So let's continue talking about minor losses, and we can talk just a little bit about parallel piping systems here. So we've been talking about these minor losses. Look here. We've been talking about minor losses being anytime the flow changes. So if I've got unions or bends or elbows or anything other than just a pipe flowing in a straight line with no connections, no changes. Anytime the flow changes, you're going to have some energy loss associated with that. So it could be energy loss, head loss, pressure loss, any form of it. Now, we talked about finding the major loss. That's the loss associated with the straight flow of the pipe, using the Darcy friction factor, function of the Reynolds number, and the roughness of the pipe. And then we talked about finding those minor losses using some kind of minor loss coefficient, which we would normally find in a textbook, or we would measure, or in a realistic scenario, or we'd find a trusted source and try to find an approximation for it. Now, if we talk just a little bit about parallel piping systems, we didn't get to that yet. So let's talk about parallel piping systems. Let's mention this here, what it says. If two or more, could be 3, 7, 200, as many pipes or conduits as you could possibly have parallel to one another. So if two or more pipes are connected in parallel, the head loss is going to be the same for both pipes, or all 3 pipes, or all 4 pipes. However many pipes are connected in parallel, the head loss, or the energy loss, or the pressure loss, all of the losses are going to be the same. Now, that might seem a little weird. Why in the world would that be the case? Now, if you've had an electrical science or maybe an advanced physics course where we talk about electricity, this is the same idea of parallel resistors. The voltage drop is going to be the same across parallel units in a circuit. Same thing here. Fluid behaves very similar to electricity in a lot of aspects. This is one of them. So let's say I've got some kind of conduit here, pipe or something like that. And let's say I've got flow coming in here. Okay, some kind of flow coming in here. We've got flow going out there. And so I've got one pipe coming up here. Let's say I've got a main pipe just right straight through, and then I've got another pipe that is just kind of crazy. Just absolutely ridiculous. I forgot to start my timer, so you're going to hear a pop here. I got to check my time. 3:20. I'm doing math in my head here. Okay. So let's say I've got pipe A, pipe B, and pipe C all flowing in parallel. Well, if we call this 1 and we call this 2, we know conservation of mass tells us that m dot 1 is going to equal m dot 2, that the mass flow rate is going to be the same in both ends of this over here. Right? Now, so here's the thing. If I've got steady flow, right? If I've got as much mass flow rate coming in as I have going out, and there's no mass accumulating within this thing somewhere, right? So if I've got a steady flow or steady state scenario, that tells me that the mass flow rate through A plus the mass flow rate through pipe B plus the mass flow rate through this ridiculous pipe C is going to equal m dot 1 is going to equal m dot 2. This is conservation of mass. Now, our theory here, as far as the losses go, what we're saying here is that the head loss or the pressure loss or the energy loss is going to be the same for each one of these pipes here. Okay. So think about it this way. Let's say we talk about point 1 here and we talk about point 2 there. Now, if the pressure right here coming out of pipe A is, let's say, less than the pressure coming out of pipe B, what's going to happen? Well, the fluid is going to try to flow back here, right? So if I've got more pressure here at the end of B than I have right here at the end of A, the fluid's going to try to flow into pipe A, as well as I've got flow coming this way. So it's going to stack up, and then eventually it's going to push its way out. So when I first turn this on, that's a different scenario. But after I've got this flowing and going for a long time, where m dot 1 equals m dot 2, the pressure difference between 1 and 2 has to be the same across here, as across here, as across all of this craziness down here. The pressure drop has to be the same, or the head loss has to be the same from point 1 to 2, no matter which path we go through. Otherwise, you're going to have backflow. Again, if the pressure here is lower than the pressure there because we've got all this craziness, so it's got to be more pressure loss, right? No, think about what happens is if the pressure here is lower because there's more pressure loss, then some of this fluid's going to come down here and flow in here. So some of the fluid's going to come out of B and flow into C, and it'll do that for a brief instant until enough fluid from C pushes it back out and everything starts going again. Okay, so it's, again, if I've got 2 or more pipes connected in parallel, the head loss is going to be the same. Okay? And so what we do is we say, well, the head loss for pipe A is going to equal the head loss for pipe B is going to equal the head loss for pipe C. Right? And so what ends up happening is we say, well, pipe A is, you've got a Darcy friction factor for pipe A times the length of A divided by the diameter of A times V squared for pipe A divided by 2G. And there's going to be a tiny minor loss here because the flow is changing. It's going through a bend here. So plus the minor loss associated for pipe A plus, again, VA squared over 2G. All right, so that's going to be the head loss for A. That's going to equal the head loss for B. Now, B is just a straight pipe. I would suggest that's just a Darcy friction factor for B, length of B over the diameter of B, the average speed of the flow through B divided by 2G. So it's just, I wouldn't even include a minor loss for B. You're going to have a loss here at the entrance and exit, but I think it's going to be pretty small in comparison to the major loss there. Now, for C, though, C is just ridiculous down here, right? So you're going to have a Darcy friction factor for C, length of C divided by the diameter of C, the average speed of flow through C divided by 2G, but there's also going to be a lot of minor losses in pipe C there. But again, what we can do is say, well, they're all equal to each other. It's the same loss for each one of them. Okay? Now, I normally don't, this is not something I would put on an exam myself personally. There's just too much algebra here, in my opinion. Unless you do, I mean, you could do it really simple, right? If we didn't have this ridiculousness of C here, if we were just looking at A and B, right, then this wouldn't be too bad. You're just going to probably have just a couple of minor losses for A, find a Darcy friction factor for A, Darcy friction factor for B, given the lengths. It's not terrible if you get rid of the ridiculousness here. Right? This would be doable on an exam problem. I'm not going to put one on exam myself personally, but assigning a homework problem of a couple of parallel pipes, that's not too bad. So, and again, when you encounter this, you just have to understand the loss for each of the pipes is the same. Okay? Now, what comes after this then is I've got an example here we'll work through. This is going to be an iterative example with minor losses. So I'm just going to pause the video here. This is a nice stopping place, and we'll pick up on the next one.